Okay, good morning. So what I'm going to do is present some preliminary hazard sensitivity and hazard feedback results based on what I've gotten from the TI team in terms of the preliminary source model. And a lot of the details of the specifics I'm not going to go into because I think over the next 2.5 days now we're going to see more detailed analysis and discussion about certain aspects of certain models and certain parameters and things of that. So this is sort of just a way to give informative results back to the TI team and for the PPRP to review to say what is important, what matters. And Norm gave a good overview this morning on sort of seismic hazard and sort of what matters is what we're trying to get at and spend a lot of time in sort of refining those. So I'm going to go through quickly. In any type of hazard analysis, of course, there's a whole nother section and a whole nother working group that's going on. We had our Workshop 3 meeting 2 weeks ago for the GMC group, the ground motion team. So for this results that I'm going to be presenting today, it's a simplified, very simplified version of the ground motion equations, prediction equations, the GMPEs, not the logic trees that were presented at the Workshop 3 2 weeks ago. As we've heard a little bit from Steve this morning, there'll be a discussion or a presentation of different SSE models, source characterizations, and then within that there's going to be sensitivity analyses based on certain features and certain parameters. That's the third bullet there. And then finally, I'll end the talk with a presentation of the tornado plots. And before I get to the tornado plots, I'll go through a simplified way in sort of explaining how we calculate these tornado plots and sort of an approach or a discussion as to what these mean and how we can sort of interpret the tornado plots. So starting off first with the GMPEs, 2 weeks ago we heard some preliminary logic trees for the different logic trees for the ground motion prediction equations for the SWUS project. That's of course including Arizona in the ground motion modeling. But if we're looking at sort of Diablo Canyon, I've selected 5 GMPEs to use for all the analyses that I'm presenting today. So 4 of them are the currently being released NGA West 2 ground motion models, and that is the ASK model, the BSAA model, the CB model, the CY model, and then the 5th model is the ASB, which is the Akar et al. Model, which is primarily based on European data. But the reason these 5 were selected were because these are the 5 of several candidates that are going into both the strike slip ground motion modeling cases and the reverse fault modeling cases. So from the ground motion team, we had to come up with sort of 2 different types of source classes that are controlling the hazard at Diablo Canyon, one being, of course, these vertically strike slip faults or nearly vertical dipping strike slip faults that are located very close to the plant. And then as well, you've got all the reverse faults that we've seen some presentations on, and we'll see a lot more in the next 2 days on reverse faults that are basically right next to the fault or the fault is sitting on the hanging wall site. Based on that and looking at the GMPEs, this is sort of a subset. What I'm doing is I'm running everything for a reference site condition of 760 meters per second for the WS-3. And along with that, some of the ground motion prediction equations require a depth to the 1 kilometer or a depth to 2.5 kilometer boundary depth. And so I'm just taking the recommended default values for those models. I'm using the full ergodic sigma, so a big part of the ground motion team working logic tree is to develop a single station sigma or an adjustment on the ergodic sigma, but for these results I'm doing the full ergodic sigma. And then I've given equal weights to these 5 ground motion models, so they each get a 20% weight. The next thing I'll sort of go over, and we've seen a good overview from Steve this morning, are the SSE models, the tectonic models. So as Steve mentioned, there are 3 primary models, one being the outward vergent. So I'm going to abbreviate that as OV in all the slides that you'll see later this morning. That's given a weight, preliminary weight of 40% in their logic tree. The next one is the southwest vergent, which is the main reverse fault dips to the northeast, and that's given a weight of 30%. I abbreviate it with SW for all the future slides that I'm going to show. And then the third one is the northeast vergent, which is abbreviated NE. So in the slides going forward, you'll see abbreviations rather than the full name. The other thing I'm going to plot on a lot of my plots is the results using the 2011 Shoreline Report SSE model. And so that's sort of a reference of a couple years ago, this was what was done for the characterization of the seismic sources. And it's an informative way of saying how did things change if we use the new preliminary SSE models and as well the GMPEs that I'm using. So the GMPEs are going to be consistent in all my presentations. So it's trying to isolate just the differences in the SSEs. This is just a quick slide that I borrowed from one of the figures that Steve sent me preliminarily, and it's just one of the cases, but it is showing sort of the different faults in the region. And as Steve went through, and there'll be more detail as it gets into these specific models, there are several different individual strands and several different features that are coming through, and I'll do a lot of sensitivities on these different features going through and looking at the results coming out. This is my list of sensitivity cases that I ran the last week and a half, and I'll be showing some results for. So the sequential order here is actually in the same order that you'll see at the end with the tornado plots. So this gives you a little bit of a preview as to what is the most significance, because in the tornado diagrams, what we like to do is we like to plot the largest spread or the largest range at the top, going down to a narrow range on values closer to 1 down near the bottom. So if I just go through them, the first one that you'll see is the recurrence. And Steve just mentioned this at the end of his last talk. That's looking at the time dependence, or the Poisson equivalent rates. And so if you remember back on his talk, he was talking about scaling the Poisson rates by factors of 2.2 or scaling it down by a factor of 0.2. And so each of the sources in the hazard runs are being scaled by that, and then the resulting hazard curve comes out. The next one that Steve also emphasized, the top 4 faults that matter, are the Haas-Gree fault. And so one of the things they had asked me to run is to vary the slip rate. So Steve had shown a 3-point distribution of the slip rate that they've come up with. Well, the question becomes, what happens if you run the base slip rate with 100% weight, disregarding the upper and the lower, and then likewise run the upper and the lower rates and see how that impacts the hazard at the end. The next one is for those faults that are characterized with a characteristic magnitude distribution, again, running the base or the middle and then the upper and the lower for the maximum magnitude. Then the next one is the shoreline fault slip rate. So again, it's the same procedure where we're given a 3-point distribution for the shoreline slip, but let's run the middle, the upper, and the lower and see how that impacts the hazard. The other one is the Haas-Gree fault dip location, and so that is changing the sort of the dip angle. And if you remember from Steve's talk, of the 3 models, each of them had a different dip angle associated with the Haas-Gree fault. And so there's a little bit of variation as to whether you think it's a 90-degree dip, 80-degree, or 70-degree dip. If you also remember back to Norm's talk, the dip angle is going to be changing the distance relative to the plant. And our attenuation curves, our GMPEs, really saturate, they turn over, so at those changes in dip angles probably won't be significant. And that's sort of, I'm previewing things, but it won't be as significant in the sense that your GMPEs, your ground motion attenuation curves, are already sort of saturating or turning over. Then the next one coming down is this range in the 3 SSE models. So again, we have the OV model, the NE model, and the Southwest model. And then I'll show on there as well a plot showing a point for the Shoreline 2011 report. The next one down is then a variation on the Los Osos slip. And then following that, there'll be the San Luis Bay slip. Then there are some other faults in this characterization of the 3 tectonic models, which are combined with, say, the 4 main players in the source characterization. But we do have a range of slip rates on those, so we varied those slip rates again, looking at the middle and the upper and the lower values. Then for those faults that have a Gutenberg-Richter relationship, Steve showed that the weighting was 90% for the WACI model and 10% for the Gutenberg-Richter exponential model. If we vary the maximum magnitude in the exponential model, we'll see how it turns out. Then the next 2 are sort of dealing with, if we look out beyond, say, the immediate area around the plant, we've got some other faults in the area, obviously. So if we look out, we've got the San Andreas out there, and as well, we've got about 151 faults that they've provided to me if you go out a 200-mile radius. And so the question becomes, you know, we've always been talking about these 4 main faults in the close vicinity of the plant that control the hazard. Well, we want to see how much do the other faults contribute to the hazard. So are we missing something, or are we capturing what's sort of important and what we need to really focus our resources on? And then finally, I'll do a short presentation on the WACI model and the impacts on that, and Norm will give a more detailed discussion on that later. And the last plot, and there'll be a further follow-up on Thursday, is sort of looking at the background seismicity. So again, this is answering the question of We've modeled all these crustal faults, we've characterized them in a certain way, but have we missed any sort of off-fault seismicity in the area? Have we missed anything in looking at that? And so I'll show a plot or two showing the importance of that, the relative importance of that. So just starting off with a hazard curve plot, I'm going to be showing several hazard curve plots, and there are several things to first note that will be consistent for all my plots. The first thing is on the x-axis, this is now normalized PSA or normalized ground motion. The reason we're doing that is it's a little bit easier to see things when I normalize them because it shifts it to a range. But the more important thing is we're actually more concerned about sort of relative changes. And so we're not, because these are preliminary ground motion logic, or preliminary logic trees and stuff, we don't want to necessarily focus on what is the absolute ground motion at 10 to the minus 4, but we want to look at sort of what is the relative change between one to the next. On the y-axis, you have annual exceedance probability. So again, if you look here, we're at 10 to the minus 4, 10 to the minus 5, and down to 10 to the minus 6. This chart is a little bit busy. It's for 5 hertz, but I wanted to show this initially to show the contribution by the different sources. And so if you look, first of all, the highest curve up here, which is the pink dashed line, that is the results using the Shoreline SSE 2011 model with the 5 GMPEs that I'm using for all of these results. And so one thing you can see is that in 2011 there was a lot of work that went into that, but it's coming up to a little bit higher ground motion values in the hazard when you look at it. And part of that, if you remember back, Steve gave a presentation talking about the weighted slip rate for the Hosgri fault. If you compare that value, I think it was 1.8 or so, 1.9. If you compare that to the Shoreline report, the weighted value for the Hosgri slip was about 2.25 millimeters per year. So the slip rates on the Hosgri, which is the most important fault, has come down, so that makes sense. The next curve down, which is a red dash with the big red dots, that's the combined. Now the combined is including 40% on the OV model, 30% on the Southwest model, and 30% on the Northeast model. So that's now combining the 3 tectonic models and the preliminary logic tree for the SSE. And you can see it's come down relative to the Shoreline model. Then below that, I've got a solid red curve, a dash green, and a dash, the solid red curve. That is now the total of just the OV model. So for a lot of the sensitivities that I'll be presenting here, rather than running 3 times the number of models for the sensitivities, we would just sort of pulled out and said the preferred right now at 40% weight is the OV model. Let's run that one for our sensitivity. So you'll see in my plots a lot of times I'm just showing the OV model, and I'm always keeping on there these 2 curves, typically the Shoreline and the combined, which is everything combined for the current SSE logic tree. But what you can see then, the next curve down is a green dash, that's the Hosgri. So this is, given the OV source model, source characterization model, what is the contribution from the Hosgri fault? And you can see, as we've seen before in the past studies for the Shoreline and other studies, the Hosgri makes up a large percentage of the total. And so that's why the Hosgri is one of the key faults in terms of characterization and impact on the hazard. The next fault down is the Shoreline, which again is a very close fault, less than 1 kilometer from the plant site. You can see it's this blue dash line that comes down here. It's less contributing than the Hosgri, but it still contributes. And then moving down, you've got the Los Osos and the San Luis Bay, which is the light dash blue line, the solid gray line, which is a little bit difficult to see here. But the only other 2 things I'd like to point out, and I'll have other slides later on in this, is I have thrown on here the San Andreas contribution, which is the dashed line here, which is this actually lowest curve coming down here, and then the regional. And for the regional, like I said, I've taken all 151 faults that they gave me and combined those into a single hazard curve. So if you wanted to see a hazard curve by individual sources, there'd be 151 hazard curves that would plot way down here, but their combined total is this sort of orange dashed line. And so from this, at 5 hertz, you can see at 10 to the minus 4, if we come across here and look down, it's several orders of magnitude down for the contribution to really even start to show up for both the regional faults and the San Andreas fault. And so that gives you an idea of sort of what are the significant contributors to the hazard at the site. If we look at the same plot now with the same curves, but this is now for 1 hertz spectral acceleration, it's a very similar conclusion. The only real difference now is that the San Andreas and the regional faults start to come up a little bit, slightly. Here's 10 to the minus 4. If you come down, it's about 2 orders of magnitude down on the hazard curves. But overall, it's the same general trend in the sense that you've got the Hosgri being the main contributor here, followed by the Shoreline and then the Los Osos and the San Luis Bay. So those, again, as we've talked about and we've heard about this morning, those are sort of the 4 main players for our plant site at Diablo Canyon. If we break things up by deaggregation now and looking at things, we want to say, okay, what's the magnitude distance contribution to the total hazard? So to do that, we have to break it up for a given annual probability level, and so for a given spectral acceleration. So this is for 5 hertz spectral frequency at 10 to the minus 4. And so we've broken up the deaggregation. Along here, along this axis, you have the distance bins. And it's a little bit different than you probably are typically seeing in the sense that I've broken it up by 1 kilometer bins. So I've done a very fine sampling on distance. And then across this axis here, I have the magnitude. And I've gone by 0.2 of a magnitude units. The reason I did this is because if you go back and, for example, look at the deaggregation plots in the shoreline report, I think they go 0 to 3 kilometers, 3 to 6, 6 to 9, and then they start stepping out larger. The magnitudes are probably half magnitude unit bins. The difference between, and I'll show a shoreline report SSE results, the difference is in this new model, we have a little bit finer distribution on the location. So for example, for the Hosgri location, there are 3 traces. There's a middle trace, there's an east and a west trace. When you do that, you get contributions that might fall into a different deaggregation bin if you had large bins. So if you went 0 to 3, 3 to 6, the eastern and the middle might fall in the 3 to 6, but then the next one, the western, might be further out, might be 6.1 kilometers, so it'd fall in the next bin. This way, if you break it down into single kilometer unit bins, you can get a better idea of the distribution. And so you can see that, as we expect, the main contribution is coming for 5 hertz at 10 to the minus 4 from these close-in faults in the moderate to intermediate to larger magnitude range. And this is for the OV source model. Just to contrast that, we have the same plot, but this is now using the shoreline SSE model. So this is the deaggregation results. It's the same magnitude and distance bins, so 1 kilometer in distance and 0.2 in magnitudes. You can see there is a little bit of a difference. So if I toggle back and forth, you can see this is more distributed here as compared to the shoreline. And this is what I was talking about in the sense that the shoreline had 1 single trace of the Hosgri fault, so everything's going to be at the same distance. Whereas in the other case, you've got a little bit of a distribution on the distance. But as Norm showed this morning, as we look at the attenuation curves, whether you're at 4.6 kilometers or 5.2 or 6.1, those attenuation curves are fairly saturated, they're fairly flat. And so the overall hazard doesn't necessarily change that much, but the distribution and the contribution might be a little bit different between the source models. If we just do the same plot, but look at 1 hertz, this is now for the OV model, you'll see what appears to be a big contrast between this one and the next one, which is the shoreline. But again, this is because the shoreline is all stacked up into this distance bin, whereas, for the OV model, it's a little bit more distributed. So the peak value here on the z-axis is the same. So visually, it might look very, very distinctly different, but it's actually just because of the fact that these peaks, this large peak here has been distributed more in distance and magnitude range. Steve?
Nick, that explains the difference in the distance distribution. How about the difference in the magnitude distribution between the shoreline and the OV? The shoreline case seems to extend out to larger magnitudes.
Yeah, that's I would expect. I don't remember if the shoreline used 90-10 on the characteristic exponential or not.
I'll look it up. We're curious about the same thing. One of the things I'm going to look into is whether or not there was a branch for a characteristic earthquake that was up in the high 7s. I remember there being some confusion about how we were putting together the logic tree at the higher magnitudes, but let me check on that. So I guess what question would I have, could that be the influence of a epistemic of a branch choice for a high MCAR on the Hosgri? Because that would put a lot of moment into that large magnitude. Again, I'll look it up.
I was going to, there may be a dilution across the several Hosgri sources so that each of them is at a lower rate. So I wonder if they're disappearing downward at the large magnitude of 7.5 that creates that prominent shoreline thing. I wonder if they're getting dissipated or spread out somehow so that they're to the right, or I mean rather to the left of the yellow peaks at 7 to 7.2. They're really there, but they don't show up because they're down at a noise level of some sort in this plot.
So I'll look into that, and I'll work with Steve on looking into that question. Just to show a fractal distribution of the hazard curves, we've been talking about, and we will be talking about the mean hazard curve, but if we want to look at the fractal distribution of the hazard curve, this is for 1 Hertz spectral acceleration, again, the OV model, given 100% weight rather than the 3 combined. And what you can see is the red curve is the OV total, and you've got the 5th, the 15th, the 50th, 85th, and 95th. Again, this is normalized PSA across the bottom. This is 10 to the minus 4 in the middle here. And so you can see this is the type of range on the fractal hazard curves. The other thing I should mention, which I forgot to go over, is in the preliminary logic trees that Steve showed, they had preferred a 90% weight for those faults that are characterized as a combination of the wacky and the exponential model. For all of my runs, I implemented the Young's and Coppersmith rather than the wacky model. So these results are all based on using the Young's and Coppersmith representation for that 90% of the wacky model. And I'll show you later that the influence of using a wacky model versus the Young's and Coppersmith is not a huge significant change. So now if we start breaking into the sensitivity analysis, I'll go through a bunch of these, and then again, like I said, I'll end up with tornado plots. This is looking at the different tectonic models. So again, we've got the 3 cases here with their weights, 40%, 30%, 30%, and as well, I've plotted on here the shoreline plot. This is now for 5 Hertz spectral acceleration. You can see, as I mentioned before, the pink one, which is the shoreline report, is a little bit higher. And then you've got the clustering of both the combined and then the individual 3 models. What you'll see, it's a little difficult to see, is that the Southwest model, which is given 30% weight, is a little bit higher than the other 2. And then the Northeast and the OV model plot very close to each other. And because of that, the combined is very close to those as well. So you can see this is the type of change. And in looking at a tornado plot, I'll be looking at differences in the ground motion. So I'll be looking at ground motion ratios later on when I show my tornado plots. This is the same plot, but now for the 3 tectonic models in the shoreline, but for 1 Hertz spectral acceleration. So you can see the same type of reduction from the shoreline study, but as well the same clustering between the 3 tectonic models. If we now focus on these additional faults in the San Andreas fault, like I said before, you can see this is what I'm plotting here is the shoreline for reference and the combined, as well as the OV total, which is a solid red, which is very similar, very close to the combined. But I've got the 2 hazard curves normalized by the ground motion. I've got the San Andreas here. It's a black line, black dash, and then the regional faults, which again is 151 faults all combined into 1 hazard curve. And you can see again that 10 to the minus 4, you're several orders of magnitude down in probability level for these 2 additional sources. And just to show what happens at 2 seconds, you can see this is the same plot, but the San Andreas has now bumped ahead of the regional faults as you would expect. So it's a little bit larger, relatively speaking, to the 151 regional faults. But again, if you look at 10 to the minus 4, you're looking that you're about 2 orders of magnitude down in probability level. So again, the San Andreas, although it's a close, large fault that's active out there, it's not a significant contributor to the hazard at the plant. If we then move to the next case, we're going to look at the variation on the Hausgray slip rate. So again, we've got the shoreline, the combined, and the OV total. And then we've got 3 branches for the 3 cases of the Hausgray slip rate. So we've got a base case, which is the dark dashed line here, which is actually very close to the combined and the total. And then you've got an upper and lower. And so you can see that those are sort of the bounding. If you look at the upper case, it actually is very close at 10 to the minus 4 to the Shoreline 2011 report. And so if you just look at the average slip rates that was used in 2011 for the Hausgray and as well for the upper and lower, that makes sense. So you can see you're getting a fairly decent size range here in the ground motion values, and that'll come through when I look at my tornado plots. If we now look at the Hausgray dip, what you can see here is, again, I've got the top 3 being the same as before, but you've got a base dip. You've got two different, I'm calling it a Hasgui dip southwest and northeast, because as Steve had shown, the dip of the Hasgui is dependent on the tectonic model, or the tectonic model changes a Hasgui dip. And so those are the differences between the three. And as Norm mentioned this morning, you know, if you change the dip, you're just changing your distance primarily. And so as you get to that part of the distance of the attenuation curve, the curves are very flat, so there's not much scaling with distance, so it doesn't have a huge impact. And as you can see, the hazard curves all cluster together, especially at 10 to the minus 4. If we then do the same thing but look at the Hasgui location, so this is again in the characterization of the Hasgui fault, there's a middle trace, a west trace, and an east trace. And again, the way this impacts hazard is it's just going to change your distance from your plant to the individual traces. And you can see it's even a tighter clustering between these three cases than it was for the dip. So if you remember back in terms of the Hasgui fault, what's most significant so far has been the slip rate change, and to a lesser degree would be the dip, and then to even lesser degree would be the location, whether you're on the middle, west, or east trace of the fault. If we then move to the next fault that's the most significant in the overall contribution to the hazard, we're looking at the shoreline fault slip rate. And again, you see the top three reference curves that I plotted for normalized PSA. This is for 1 hertz spectral acceleration. You can see there's a distribution as well on this, on the slip rates. In this case, the upper shoreline slip rate does not push it up to be equal to the, or approximately equal to the shoreline report hazard curve. But if you remember back, the shoreline is not as significant of a contributor to the hazard at the plant as the Hasgui is. So you can see you've got a little bit of a distribution. And in looking at these normalized hazard curves, the thing to remember that I'll go through at the end is looking at the tornado plots. So you want to look at a given probability level, like 10 to the minus 4, sort of the range in the x values. And that's the range in the ground motion. And so at the end, we'll be showing you ratios of those values. If we now look at the Los Osos slip rate, it's quite a tight clustering of the hazard curve. So the change in the slip rates doesn't have a huge impact on the hazard. Again, this is for 1 hertz spectral acceleration. The San Luis Bay fault slip rate, again, is very similar to Los Osos in the sense that if you vary the slip rates to the base, upper, and lower cases, you get almost no change in the total hazard. And this total hazard, I should say, is not just the hazard from the SLB fault. It's actually the combined, but modifying the individual contributions for the SLB fault based on their slip rates. Now, for the other faults in the area that are linked up to the 4 main players, you can see there's almost no change here. And again, you'll see that in the end when I show my tornado plots, that the factors, the ratios, and ground motion change are going to be 1. Then there are a couple of variations for the Los Osos slip rate and the San Luis Bay slip rate that they asked me to run. One is that because the different tectonic models, the OV, NE, and SW, have sort of a preference. For the Los Osos, they said, well, run the OV model except for the slip rates for the Los Osos, swap it out and use the characterization given in the NE model. And then you'll see on the next slide, it'll be the opposite in the sense for the San Luis Bay fault, use the slip rates provided in the SW model. And so it's sort of a switching of the slip rates of the characterization for those specific faults. So it's a little bit different than the previous Los Osos SLB fault slip rates that I showed before, because that was just for the OV model. So it's a cross-model propagation of the slip rates. And so you can see here for the Los Osos using the slip rates characterized in the NE model, you get a little bit of a distribution. For the SLB slip rates characterized by the SL, you get, again, a little bit of distribution. It's a little bit higher here. And if you remember back, I had said that the SW model tends to be a little bit higher overall relative to the NE and the OV model. And so that's what's going on here. You're getting a little bit higher. Next, I'll move on to the maximum magnitude. So this is for those faults that are characterized with the Gutenberg-Richter relationship. There's an associated maximum magnitude, and I was given 3 values, middle, upper, and lower. And so again, in the same sequence, the same way, I'm running hazard using the middle, running hazard using the upper, and then the lower magnitude. And you can see there's very little change in the hazard for that. Then if we look at those faults, and again, as I mentioned before, I didn't run the wacky model per se, I ran the Youngs and Coppersmith model. If I randomize, or not randomize, if I vary the maximum magnitude of the boxcar, and again, I was given 3 values, so if I run an upper, a lower, and a middle, this is the sort of impact. And so you start to see there is some change at 10 to the minus 4. By the time you get down to 10 to the minus 5, there's really no change, and I'll come through in the tornado plots at the end. And then finally, this is the wacky model, the implementation of the wacky model, and Norm will go through a more detailed presentation on this later in the workshop. But for 5 hertz, you can see what I'm doing is there are 2 B-tail distribution, or 2 B-tail values that I'm using, and this will be presented later, but basically 2 end members, one with a value of 1.2 and one with a value of 0.5. And so if you remember back to Steve's plots, that sort of is the slope of the Gutenberg-Richter part that's beyond the Youngs and Coppersmith boxcar characteristic event. And right now, for these results, I'm using the fault displacement by Wisnowski, the 2008 model. What you can see out here is that for both these curves, the 1.2 and the 0.5, they basically fall right on top of the OV model. And so this is the OV model with the Youngs and Coppersmith, as opposed to swapping out the 90% weight on the Youngs and Coppersmith using the wacky 1.2 and the 0.5 model. So you can see for this case at 5 hertz, it really doesn't make a significant difference. As you get out to a little bit longer periods, it does start to show up. You do start to see some separation on the hazard curves, but it's not a large, significant separation. Then finally, I think this is my last normalized hazard curve before I get to my tornado plots. The question that I'll be talking about on Thursday in more detail is the background seismicity. And so as all this work has gone into characterizing the crustal faults in the region, the question is, are we capturing everything? Are there events that are occurring off of these faults that are not being modeled? And so if we look at the seismic catalog that's been developed and just updated that Norm gave me for the region around the plant, and we run that in the hazard code, this is a contribution. And so you can see out here, I've got the 3 reference curves again, which is the shoreline, the combined using the 3 tectonic models, and then the OV total out here. Again, this is normalized PSA. I've now done 3 decades because to get this background curve to show up, I had to do that. I'm down to 10 to the minus 7, so you can see if we go 10 to the minus 4 and keep going down, we haven't reached it at 10 to the minus 7, so we would need to keep going down further and further before we can actually add this back up vertically into the total hazard. So this is showing at 5 hertz that the background seismicity is not a significant contributor. Then finally, the last one, I was misled. I have one more, I think. This is it. This is the recurrence. This is the time dependence. And so as Steve finished his presentation on talking about, we take the Poisson equivalent rates and we scale them up by factors of as high as 2.2, some of them 1.8 for some of the fault segments, and some of them as low as 0.2 or 0.4, somewhere in that range. When we do that, we again have the 3 reference curves. We now have what I'm calling the Poisson, which is, of course, will be equal to the OV total, because that's assuming a Poisson. And then we've got a lower and upper curve. And so here you're starting to see a big distribution. And so it's not symmetric because the scale factors are not symmetric, but we're starting to see a big impact on the hazard in ground motion if you look at the 10 to the minus 4 level. So just quickly before I show my 4 tornado plots, going into how we calculate these tornado plots and these ground motion ratios is given a set of hazard curves that we're looking at, and this is just a previous slide, but I've added a couple more curves on that. We want to look at a certain probability level. So let's say if we look at the 10 to the minus 4 level, which is this blue horizontal line here, we go over and we find our reference base case. So in this case, it would be the OV total or the, as sort of our reference, which is equal to the Poisson. And we go down and we say, okay, what's that ground motion? So it's just over a normalized ground motion of just over 1g. And then we say at that same probability level for a given 1 hertz spectral acceleration, what is the ground motion for the other curves we're looking at? And so if we want to look at, say, the upper curve, which is this gray dashed line up here, which is actually close to the shoreline, we would go over at that probability level, come down and read off the ground motion value. And so we'd be a little bit higher than the reference. And likewise, if we did it for the lower, we'd do the same thing. We'd come down and we'd be a little bit lower. And so what we do is we calculate ground motion ratios. And so we calculate ratios of the upper to the reference and the lower to the reference, such that you can look at it and say, well, if I have a value greater than 1, in my ratio, then that means the hazard curve will be higher, or the ground motion will be higher. And if it's less than 1, then the ground motion will be lower. And so that's the way to look at it. Then when we do that, we put them all and we rank these. And so that's why they're called tornado plots, because it's supposed to look like a tornado. It gets small at the beginning and sort of blossoms out as you go up the cases. So I have 4 sets of tornado plots that I'm going to show. They're both for 5 hertz and 1 hertz, and 10 to the minus 4, 10 to the minus 5. The individual sensitivity cases I've listed here on the left, they'll be consistent from plot to plot. The things that will change will be this actual distribution of these ground motion ratios. And so if I go through them from bottom to top, we've got here the background. So this is a factor of 1 means that the hazard, there's no change in the ground motion value, and so relative to my base case. And so in all of these tornado plots, what my base case is, it's the OV fully weighted. And so this is going to show the sensitivity on certain aspects within the OV model rather than the combined all 3, because it would have been 3 times as many runs to do the hazard analysis, and the OV turns out to be very similar to the combined total. So again, as I had showed before in the normalized hazard curve, if you add the background seismicity, there's really no change on the ground motion value, and so you would expect and you get a factor of 1 here. If you look at the Wacky model and replace the 90% characteristic Young's and Coppersmith model with the Wacky model, again, you get almost no change. Numerically, there's a slight difference, but visually, it's just basically a factor of 1. Again, if you add the regional faults, 151 regional faults, you get a factor of 1. If you add the San Andreas for 5 hertz at 10 to the minus 4, you get a factor of 1. Maximum magnitude, there's really no change. The other fault slip rates, no change. San Luis Bay slip rate, Los Osos slip rate. You can see there's a little bit of a distribution here, but again, you're pretty closely tied to a factor of 1 in ground motion ratio values. The Hosgri slip location, you don't get much variation. As you start moving up now, you're starting to see a little bit of a dispersion between the 3 cases. So again, these are 3 points because I'm running a middle, upper, and lower value. So I get 3 points here. You can see this is the San Luis Bay slip rate, the Los Osos slip rate for the different 2 tectonic characterizations of those slip rates. This branch here right now, the tectonic SSE, this actually has 4 points. So this lower point has 2 points, and then this upper one, that's the shoreline report. So if you remember, my shoreline curve was always higher than my other combined ones, and so that's why I'm getting the highest ratio. So if you wanted to look at just the sensitivity for the 3 SSE models, just eliminate this upper point and look at this distribution here. So you can see that with the preliminary weights of 40, 30, 30, and the source characterization that I was given, there's this type of distribution which is comparable to, say, the Hosgri dip. And then as well, here's the shoreline slip, and we're starting to get a little bit larger spread, characteristic magnitude, and then finally the last 2 on the top are the Hosgri slip, and then the time dependence. And so this is the, I didn't plot on here the value of 1, which would be the Poisson assumption. But this is about 15 to 20% increase, so it's a factor of 1.2 roughly, and this is 2, 3, 4, 5, 6, about 0.7. And so that's for 5 hertz at 10 to the minus 4. This is for 1 hertz at 10 to the minus 4, and again, it's the same sequential order. So if I toggle back and forth, you can see especially for these values down here in the lower part of the tornado diagram that are close to 1, there's really no change. Whoops. But as you get up here in the top, there's a slight change in the upper part of the tornado. Then if we move to 10 to the minus 5 at 5 hertz, it's a little bit narrower up here. Again, this is the shoreline report point up here, not the 3 individual source models. And then this is 1 hertz at 10 to the minus 5. And again, it's very similar. I've lost my 1 value down here, but that's the background, so that is going to be equal to 1. But you can see this is the type of distribution that you see from the different sensitivity analyses. And I think that's what I have.
Can I ask a question? If you could please put up the tornado plots. For the recurrence sensitivity, is that correlated in the sense that all of the faults have an equal Poisson equivalent ratio of 2, or all of them have a Poisson equivalent ratio of 0.2?
Yes.
Okay, so that really is the extreme. One of the things we should have considered was adding it to the variability of each slip rate category. That would have been another choice, right? So we would see the effect if all of the other faults had their recurrence, that were closer to a Poisson equivalent of 1, and we looked at each rate behind.
Right, yeah.
So to visualize that, we could just stretch the Hosgreaves slip even more, stretch the shoreline slip rate even more.
Yeah, so you could combine those two and
Yeah.
do additional sensitivities.
Okay. The other question, one of our, because our slip rates are preliminary, we're really waiting on reports to be finished and to evaluate the new data. One of the tasks we were hoping for would be to take this shoreline report and to scale those slip rates to match the weighted mean slip rates in our model. And the purpose of that was there are really big differences in the approach to the models. One was very much centered on characteristic large magnitude earthquakes, where ruptures were not allowed to link up and get really large. And just to isolate that effect of this fundamental shift in our approach to the SSC and divorce that from any slip rate difference. Have you been able to do that, or could you do that during this meeting? Not today, but
Yeah,
I don't know how much of an effort.
I should be able to look into that at least
Okay,
and get back to you on that.
great.
Yeah.
And evaluating the wacky model. Norm will give the proponent expert presentation then. We'll have a slide to show the PPRP of what a starting point logic tree would look like, but that's really running blind. I think we can develop that and share that with the PPRP after we see Norm's presentation, and we can evaluate our preliminary logic tree for that and show that to you guys later on. Shoot.
Another question, just sort of as our eyes are drawn to different parts of the hazard curves, I assume, just going back to the requirement of 5054F requires that the GMRS using Red Guide 1.208 be compared to the SSC. And so that obviously 10 to the minus 4, 10 to the minus 5 is the area of interest. You mentioned going to low frequencies or going to 2-second periods, a half a hertz. Do you go to anything else? Is there anything in the plant that's sensitive very long period motions that would change any results here from what you've seen?
Maybe Norm would know what the...
For this study, we will go longer to 5 seconds, just for completeness, but really there's none of our safety-related equipment is out at those very long periods. But we will create a full spectrum. So I think our focus here needs to take you all the way out to 5 seconds as well.
Yeah.
So Nick, in the wacky model, there's partitioning of moment between the three phases of the model. Could you briefly just speak to the process that led to that? Because I'm hearing it's right there in the basement in terms of its effect. If you gave more weight to the biggest earthquakes or the characteristic bit or the... Could you speak to the weighting of the three components of the wacky model and in terms of moment rate?
Let me try to answer that for you, why it shows up so far down there. Remember, so this model is going to allow some link ruptures to occur. Okay, and the constraint on how frequent those ruptures occur is based on the coefficient of variation of a slip at a point from Hecker's paper, and I'll describe that this afternoon. But you're back to the case here, we're going to make bigger magnitudes. But our model, the ground motion models have all hit saturation now. As we go beyond 7 to 7.5 and to 8, there is almost no change in the ground motion. So all that you're really doing on the effect of the hazard is changing the recurrence a little bit. And the rates at which those are happening is small. It's maybe an order of magnitude lower than the rates, or more than the rates of the characteristic part. So now you're changing, the ground motion's essentially the same, and you've basically reduced the recurrence by a little bit, but not very much. And so the net effect is you can't see it in the hazard.
Yes, I completely appreciate the ground motion component. I'm thinking in terms of making sure we know how to defend that partitioning, and you're describing that, and you'll do a great job of it. So
Yeah, wait for
life's
this
good.
afternoon on how we did it. But
Yeah, just to make sure it's more of a bases are covered thing, because I know those events are so rare and they consume so much of the slip, is that they're almost like taking earthquakes out.
that's the net effect. If anything, you reduce hazard a bit because you make a really big event. Doesn't change the ground motion much, but now choose it more of the moment.
Right.
So, I have an additional question for
Mm-hmm.
Nick that's similar to Steve's question on recurrence. The characteristic magnitudes sensitivity that you ran,
Mm-hmm.
are those also correlated? Are we looking at the distribution between all faults at their upper end
Yes.
together?
Yes, yeah. So there could very easily be several combinations of things off of this that can be run.
Thanks.
So does, in terms of what's significant, then, in terms of the wacky model maximum magnitude, other than optics that we want to consider large linked ruptures, is there really no value in considering these large linked ruptures to characterizing hazard at the site? It's not really significant.
It is not significant in a probabilistic hazard analysis for the reasons that we've talked about. The ground motion doesn't change much. And if they're rare, their rates aren't changing things
Right.
very much. So that should not be the focus of your discussion during the next 3 days. Is that a straightforward enough answer for you?
No, so it's other than the optics side, it's not significant.
If we were located a much further distance away,
Yeah, it would
then
be.
then this would matter more.
Right, so this particular site, that's the explanation. So another question on the 3, when you tested the outward vergent, northeast vergent, southwest vergent, and we see some difference. In particular, southwest vergent is giving somewhat higher hazard, maybe 10 or 20% higher hazard. Why? What part of the model is it that's producing the higher hazard?
I don't know yet. I haven't had a chance to dig into those.
I mean, we have a feel, I think, for what it is, but it would be nice to know
Yeah.
explicitly.
And to clarify, I'll do this one. On max magnitude, that sensitivity was where we gave full weight to GR. Is that correct? Do we have a sensitivity where we gave full weight to Gutenberg Richter?
I don't have that.
We don't have that.
Yeah,
Okay.
yeah.
All right. That would be great to see. So that one with max magnitude, that was the low, medium, or high value from the branch.
For the Gutenberg
alternatives.
Richter, which is only 10% of those faults that are characterized.
Okay, so that's showing the contribution from just a 10% effect.
Right,
Okay.
yeah. So you wouldn't expect that to be a big
Yeah.
shift.
Right. And then for characteristic magnitude, just to confirm that we're seeing the same pattern from earlier sensitivities, is the leftmost circle the largest characteristic magnitude? What the pattern we've seen before is the larger the MCAR, hazard gets reduced because we're consuming more moment.
Right, and so that is true. Because
Okay.
you can see here, the upper is this gray dash line here, which will give you a lower ratio, ground
Okay.
motion ratio. So
Yeah.
that's consistent.
Okay, circling back also to really wanting to look at the shoreline with our current, preliminary model weighted mean slip rates, the shoreline model systematically has lower MCAR values compared to what our preliminary model has. And so we're really interested to see is that effect of that choice and approach to magnitude distribution. So just for the PPRP, that's also structurally, we approach the model in a different way, and we found that our choices of the MCAR have tended to grow as compared to the choices of MCAR for the shoreline report. The shoreline fault itself is a very good case in point. Right? That's just something we should keep in mind as we're looking at magnitudes that we set.